Welcome back to the lecture series on bioenergy. So, in the last class we talked about the fluidized bed gasifiers, and before that, rather earlier to that, we talked about the fixed bed gasifier. So, today what we will do, we will talk about the performance of the fluidized bed gasifiers, and from there we will move on to talk about how these gasifiers are used for fuel in the vehicles, motorized vehicle. Okay. To start off with, so essentially what we will be doing today is operation and performance of fluidized bed gasifier. Operation and performance of fluidized bed gasifier. So, in terms of its performance, what are the, first we will discuss what are the major operational challenges. What are the major operational challenges? Operational challenges. So, in terms of the operational challenges broadly, there are several points what we will be dealing with. Broadly, you have to realize when you are transforming biomass directly to a gaseous product, there are a lot of big organic molecules which are getting broken down by cracking and several other processes. And many of these molecules in one step or two step cannot completely disintegrate. Instead, they form a lot of tars, and these tars, depending on the temperature of the reactor vessel, kind of condenses. That is one of the major problem, and as this tar condenses all along the walls, along the tubes, this tar gets deposited. It is just like what happens in our blood vessels, you have the deposition of fats and everything which kind of create clogging. So, similarly on the reactor vessels, the reactor vessel surface along the tubes, connectors, you have lot of deposition of the tars, and that led to a lot of sludging and all those other things. So, we will come one by one. So, let us put across the major operational challenges. In terms of the major operational challenges, the first one is the slagging. Slagging of the bed material due to ash content of the biomass. Slagging of the bed material due to ash content of the biomass. So, higher the ash, there will be more slagging. Ash content of the biomass. Okay. The second problem in the same line one comes across is alkali metal content, which is fairly high in herbaceous plant, leads to this slagging. Alkali metal content, and this also help in higher tar formation. Alkali metal content which is fairly high in herbaceous plants lead to more ash, more tar and all other impurities, and of course, this will lead to more impurities. impurities. Okay. Now, one of the ways by which you can counter the slagging is how to counter slagging. So, it is kind of a trade off, as you will see. You can, one approach is lowering the temperature, but if you lower the temperature, you will realize what will be the challenges which is going to come in terms of tar formation. Lowering the temperature is one technique. Lowering the temperature of the, basically here in the temperature we talked about the bed temperature where the reaction is happening, but then that leads to, if that is happening, there will be a increased char formation, from which all these things have to be removed, all the impurities have to be removed. And in terms of the gas, quality of gas, one has to quantify what are the impurities which are present or which arises out of post gasification. The impurities could be classified, yes, okay, impurities could be classified as particulate matter, one of the big source of impurities. Second, as I am mentioning, is tar content. Third, you have nitrogenous compounds or their derivative, nitrogenous compounds plus their derivatives which are formed during this whole gasification process, which of course leads to the reduction in the calorific value. You have lot of sulfur compounds which are derived, then you have alkali compounds. Okay. And these three, the nitrogen, sulfur and alkali, they fall under the trace impurities. So, all this blue what you see out here, they fall under trace impurities. Okay. Now, we will briefly talk about these 3 points, the particulate matter, tar and some of these compounds which are present there. Okay. In terms of the particulate matter, so this is one more thing I wanted to highlight here for all these impurities. So, most of these impurities has to be basically cleaned up, okay, cleaning, and this depends on what kind of cleaning you are doing, what is the temperature of the gas, whether it is a hot gas or it is a hot or cold gas, okay, and what are the relevant disposal issues which has to be taken into account. And we will come one by one into this matter, what are the different kind of particulate matter which are generated and how you can get rid of it, what are the compromises you do in terms of the tar formation and how you can get rid of that stuff, and what are the compromises we do in this whole process. To start off with particulates. Okay. In terms of the particulate matter, we are having two kinds of particles which are forming, ash and the char particles following the charring in complete combustion. So, it has been observed in the fixed bed reactor, the particulate matter formation is much less as compared to fluidized bed. So, in other words, your particulate formation will be higher when you are dealing with the fluidized bed reactors. Okay. And particulate is removed by conventional cyclones if the particulate size is. So, what are the removal technique of particulates? If the particulate size is say more than 10 micron, particulate is more than 10 micron, it could be removed. I am just showing the negative sign here, or removal, just for no further confusion, removal by conventional cyclones. You have already exposed to the cyclones where there are a lot of, there's a reaction is taking place by the movement of all the reactants, okay, conventional cyclones. Whereas, if your particle size is less than this, or rather below 10 micron, then the option is different. In that case, you will be needing filtering devices, you will be needing filter bags, you will be needing sintered ceramic metallic candles, sintered or ceramic metallic candles. And most of these technologies have an efficiency of around 99%, which it can remove. Filter operation temperature is very critical here. Filter operational temperature. If filter operational temperature is more than 500 degree centigrade, you get a higher efficiency, which is approximately 99%, what I mentioned you. But if it is lower than this, then you land up with a next problem which we will be dealing with is tar condensation. As I was mentioning you earlier, that if you reduce down the temperature, all those big molecules which fail to crack accumulates at that lower temperature, and kind of with little bit of a fluid which is available there, they form kind of a sludge or kind of sticky stuff which sticks onto the walls. So, if you reduce down the temperature out here, this is the problem you face. But again, if you have the high temperature, then you have the problem of storage of the gas. So, it is always a trade off at what temperature your output is coming and what temperature you are running the reaction. That will inevitably decide the performance of the reactor at which it is working. So, keep that in mind. There is no absolute rule, there is no absolute protocol which you can follow, you can say this is perfect. So, depending on the kind of biomass you are having, depending on the kind of economics you are having, you have to decide that at what temperature, at what pressure you are going to run the reactor. And of course, it will have its own trade off, it will have its own advantage and disadvantage, you will be coming along with it. Okay. So, next problem is the tar content. So, this is one serious problem most of these gasifiers suffers from, tar contents. Okay. So, tar condenses at a temperature less than 500 degree, condenses at a temperature of less than 500 degree centigrade. And what essentially happens, as I was trying to verbally trying to tell you, say for example, this is the vessel where the reaction is happening, or these are the connectors where things are moving. So, what will happen along these walls, you will see there will be deposition of tar like this, they condenses and they can clog. There will be a lot of inefficiency which will arise because of this kind of tar deposition on the surface, and this has to be either scrapped or by using different techniques you have to kind of get rid of it. tar deposition. Okay. So, this is a perennial problem what you deal with. So, and this also further tar deposition leads to the second problem it leads to is the hinders removal of particle, hinders removal of particles. Okay. Now, post this, what are the ways? Tar reduction or removal? Tar reduction / removal. What are the techniques which are being followed? One of the thing is that tar could be cracked further, is basically you are breaking the molecule, cracking of the tar to low molecular weight compounds, low molecular weight compounds. Using either. So, this whole cracking could be done. There are two techniques by which you can do. One technique is a catalytic technique which is called catalytic cracking. Catalytic process. The other one is called a thermal process. Now, in terms of the catalytic cracking, you can use different kind of catalytic agents which are catalyst which could be used, which includes you can use olivine, you can use platinum, you can use dolomite. There are several catalysts which are being used and it functions around 800 to 900 degrees centigrade. Whereas, in terms of thermal process which functions at around 900 to 1100 or 2000 degrees centigrade, this thermal cracking. Thermal cracking is more to do with like you are exposing these molecules at a very high temperature where the molecules cracks out and forms lower particles, lower size particles, and then those are filtered out. Okay. And there is one more thing here, it is worth mentioning that whatsoever way you do, you can reduce the particle size and everything, but then you will have to very continuously change the filters. Or there is another thing which is very critical. Once you do a thermal cracking, the next step what leads to is that you have to cool the gas, because you are raising the temperature all the way to 1000 degrees centigrade. So, now you have to cooling the gas. So, cooling the gas is a challenging task here, and that you do, cooling the gas to around 60 to 80 degrees centigrade. You have to use, this is 80, okay, 60 to 80 degrees, that you use using water. But when you are using, or rather you use electrostatic precipitator, electrostatic precipitator. When you use electrostatic precipitator, you are capturing a lot of aerosol, but in doing so, you are polluting the water which are using for this process. And if you do so, then you land up with another set of problem, that now you have to purify that water. So, in other words, this whole research or this whole area of development is a very interdisciplinary area. So, let me add here. So, when you are doing it, so you needed a water purification assembly out here, because water is a very prized commodity, water purification, because you are really contaminating the water. So, you are realizing there is no one way, and one has to think from the very beginning of the course. Now, we are at the fag end. I have been repeatedly telling that one has to think very holistically whenever we think of following or emulating nature. So, this is another way. You have the gas, you wanted to get rid of the tar. In order to get rid of the tar, you have two techniques, either you follow the catalytic route or you follow the thermal route. But whichever route you follow, you are raising up the temperature of the gas to 800 to 1000 degrees centigrade. But then at that temperature, it is tough to collect the gas. So, you have to bring down the temperature. When you are bringing down the temperature, you are using it while passing it through water. But while you are passing it through water, water picks up all the different aerosols which are present there, and in that process the fresh water now getting contaminated with all these aerosols. So, your next challenge is that on one hand you really got the gas right, but then you have to purify this water. So, you are realizing that there is no absolute route, there is no absolute process by which I can say, okay, this is how it is going to work. So, one has to think very, very, very rationally how we can optimize these processes next centuries in order to meet our fuel demand. Okay. Now, coming back to the third set of contaminants or particulate matter which are present there, which includes your nitrogenous waste. Okay. So, we will be talking about nitrogenous waste, we have sulfur waste, we have chlorine, which mostly comes in the form of HCl or hydrochloric acid. This comes out in the form of ammonia, sometime hydrogen cyanide. Sulfur comes in several forms, H2S and other product, and you have a lot of this sodium and potassium which are present there. So, most of these are filtered after cooling the gas. We have already discussed about it. Okay. Filtered through cooling the gas, whereas HCl could be removed. This negative sign shows the removal. Absorption on active material, absorbed on active material like calcium oxide or magnesium oxide. Further, this could be removed by wet scrubbing. There is a technique called wet scrubbing. Okay. In aqueous solution or in water, wet scrubbing with water or some aqueous solvent at a temperature of 50 degrees centigrade. Okay. You can also remove the ammonia and all other things using water scrubbing. So, if you look at it, the rate limiting point out here is water, you need active materials, you need filters. So, you will realize in order to emulate nature in the form of forming gases, you have to go through this whole route of ensuring all these raw materials are being taken care and series of different things. Okay. So, this is what I wanted to cover in the gasification section, and that pretty much brings us to the very end of it, of all the different processes. So, what we will do in our next class is we will summarize this whole thing. Before summarizing, we will talk about one small fragment. We will talk about how these what is the genesis and what is the history of this gasified fuels, when it all started and where all it could be used, and we will give a schematic. After that, we will talk about a summary of what all we have covered in the course, and we will talk about the concept of the biorefinery in our next class. Okay? Thank you.